So, hi and welcome everyone. In today's lecture, we will continue talking about the big picture of physical layer security techniques against wireless passive eavesdropping. In the last lecture, we talked about SINR-based keyless approach. In today's lecture, we will mainly focus on complexity-based key approach. Now, we need to understand the concept of this approach, the main concept and how it works. So it's extracting random keys from the channel of the legitimate parties to manipulate the data at the upper layers, bit level, or lower physical layer, symbol level. So this is basically the main concept of complexity-based key approach. Now let's just explain this by drawings and visualization for you to understand how this really works in real life scenarios. So we open the bin over here and we can use blue color. So the basic idea here is we have a transmitter and we have a receiver TX and RX, and I told you we have a channel between them. Everything is based on the channel in physical layer security. This is called H. So both the transmitter Alice and the receiver Bob they try to measure the channel, to estimate the channel, but to estimate the behavior of the wireless medium between the transmitter and receiver. And let's say this estimated it to be like this, and this has to estimate it exactly the same, uh, close or equal almost to the channel that the receiver estimated if they are using TDD system, time duplex system. So the channel here will also be the same at the transmitter side. Almost, I mean. So in this case, the receiver uses this channel to extract some random bits, uses some techniques to extract random bits. The same algorithm that he uses at the receiver, the same algorithm that's used at the receiver will also be used at the transmitter to extract a sequence of random bits, and here a sequence of random bits. So this becomes like a shared key. This sequence, and this sequence becomes like a key, shared key at both the transmitter and receiver. Now, why it becomes like a shared key? Because both the transmitter and receiver, they are sharing the same channel. When they are using TDD system, time division duplex system. Why time division duplex system? Because I told you in time division duplex system, the uplink from the transmitter to the receiver and the downlink from the receiver to the transmitter, they use the same frequency, and therefore the channel response will be almost the same. Okay, so this is the main concept. Now this sequence of bits can be used to manipulate data at the application layer, upper layer, or at the physical layer, the symbol level. Now, what do I mean by symbol level? For example, after modulation, you will have your data in complex values. Complex values, which means that each number represent a real and imaginary part. So you could use these bits to change the phase, to change the real part or the imaginary part, or the amplitude of the value of the complex number, or the phase of the complex number. And this will produce a random sequence that can be used to manipulate your data and to make it secure and robust against eavesdropping attacks. So this is the main concept. What are the enabling techniques in this case? You have channel quantization and sharing techniques, which exploit channel reciprocity property and its variation at both the transmitter and receiver to extract secret keys. So the techniques are basically channel quantization. Now we need to understand what's the quantization. How does it happen really in real life scenarios? So let's assume the transmitter and receiver, they estimated a channel that looks like that. Okay, so both the transmitter and receiver, they have copy of the channel. So what they do now, they try to quantize so that they can extract random bits. What's the process of quantization? Quantization basically discretizing the amplitudes, the value, the amplitudes of the signals, or the power of the signals on the y-axis. So what does this mean? How do you do that? You have a reference level for the quantization, which we consider it normally to be the zero level. And then if you were to quantize this, let's say this is the maximum amplitude A, and this is the lowest amplitude 0 or minus A, and you need to quantize this signal, then the number of bits that can be assigned for each level depends on what? Depends on how close these horizontal lines are. The closer they are, the more fine the quantization is, and therefore the more bits you will generate. But the more it will be more susceptible to errors. So for example, this level, if I were to quantize this into how many levels, let's say 1, 2, 3, 4, let's say 8 levels. In this case, I can put, if I have 8 levels of quantization, which means 8 horizontal lines, how many bits I need for each level to represent that quantization level? I need 3 bits, because 2 to the power 3 is equal to 8. So 3 bits. So I start from here, I assign 0, 0, 0 to the first level. And then after that, 1, 0, 0, 0, 1, 0, 1, 1, 0, and so on until I reach 1, 1, 1. Okay? And then we know in this digital systems, we don't have continuous signals in times, but we rather have them what? We have samples. We take samples. We don't send the whole signal as analog. Why? Because if we were to send the whole signal as analog, it will take too much memory, too much bandwidth. So instead of sending the whole signal, we can send only samples of it. And if I draw lines between these samples, I will be able to recover the signal that was sent or transmitted. So these samples. So if I come to the first sample, this sample is closer. It seems that it's closer to this level. The first sample is closest to this level. Then I look for this first sample. What's the number? What's the sequence of values? The values that represents this level. We said the first level 0, 0, 0, and then 1, 0, 0, and then let me just 1, 0, 0, the second level. The third level is 0, 1, 0. The fourth level is 1, 1, 0. And the fifth level is 1, 0, 1. So this value then for this sample in the sequence number that I'm trying to generate, I will put what? I will put 1, 0, 1. This is the first value representing the first sample in the signal. And then you come to the next sample over here, and you put what you see where it's closer. Let's assume it's a bit farther here, and let's assume it's closer to this. You put the value here, and you continue until you finish until you finish all the samples. You take the values of all the samples, put them inside the sequence, and this sequence consequently, because the same channel is available at both the transmitter and receiver only, and the channel is TDD, and there is time reciprocity property, and we have discretization, quantization in the amplitude domain, and the channel is shared between the transmitter and receiver. The extracted sequence here can be used as a secret key that can be used in encryption and decryption. Okay? A secret key that can be used in encryption and decryption. Any questions about this quantization? Clear? So, this is an example where you can, in the final, you might be asked, I can bring you a signal, for example, like this, and tell you, please quantize the signal and extract a random key from it. So in this case, you should be able to extract it. Okay, any questions so far? Is it clear? Everything is fine regarding this approach of quantization that we use to extract random secret bits? If everything is okay and fine, we can continue. We understand channel quantization. We understand the word quantization. I told you in this course you will face so many new terminologies, technical terms that you see them maybe for the first time. That's why I focus too much on making sure that everyone understands the meaning of each and every new terminology, a new concept, a new abbreviation, or a new technical term. Because if you don't understand them, you will not be able to visualize in your mind what's going on. But once you understand the meaning of each of these new terms, you will be able to link them and visualize them in your mind. So this is quantization. What we explained just right now is quantization. What are now? Let's discuss the merits, the advantages of this kind of approach. So the first one, it solves key distribution problems. Why does it solve the key distribution problem? Anybody knows? Because we don't need now a third entity or a separate server that's responsible for distributing keys and sharing them between the transmitter and receiver. A trusted entity, third party, and manage the key sessions, updating them, renewing them, terminating them. Instead, we have a common channel that's continuously changing based on the wireless medium between the transmitter and receiver, and the transmitter and receiver have access to it. The TX and RX can continuously measure it and extract random bits from it. And once they extract it, since it's a common thing between them and it's estimated, the values estimated from it are almost exactly the same. So we don't need a third-party trusted center to distribute the keys for us as transmitter and receiver. That's what we mean by it solves key distribution problem. I think of the wireless channel as a source of randomness that I can always probe or measure and get random data, random sequence numbers that I can use to manipulate and encrypt and decrypt my data, the data that I want to send confidentially, and make it robust against eavesdropping. So the channel here act as a source of randomness, a natural, this is very important, natural source of randomness. It's not like artificial. And I can always measure it and produce new sequences from it. That's what we mean by it solves key distribution problem. What about the second point? It provides secrecy even if Eve has better channel conditions than Bob. That's very important. You remember when we talked about the techniques here, when we talked about the techniques related to SINR based keyless approach, what did we say? The first requirement, when providing secrecy is possible when Eve's SINR is naturally due to the channel quality or artificially due to a special technique made lower than Bob's SINR. So this is a preliminary, this is a prerequisite, this is a condition. Without it, we cannot even have security or providing secrecy. But here, it's not a condition at all. It's not a condition because the random sequences that we extract usually, we 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 take them and we extract them, generate them from the small scale fading channel, not the large scale fading channel. So having the receiver close or far from the base station or access point doesn't matter much as long as we have a rich scattering channel. So that's a very important point. The third merit is it provides authentication. Okay, now this is since it can extract a key from both parties, transmitter and receiver. So this key, we know all authentication processes and techniques, they depend on using a key that can be used as public or private or a common shared key. In this case, this also can be used for authentication. So the approach here can simultaneously, in parallel, be used for both providing confidentiality and authentication, which is excellent. You kill two birds with one stone, two advantages with just one technique. So these are the things related to the advantages of the category called complexity-based key approach. Any questions so far? Everything is fine.